So hello everybody online and here at University of Ljubljana. Welcome at our last final Sustainaware webinar on carbon dioxide removal. We are honored to host Victor Josa, our colleague and consultant for our project, Sustainaware. So just a few words about Victor. Victor's experience roots from the youth policy lobby on of the UN Climate Change Convention and the World Health Organization, with a focus on innovative education and outreach for climate action. Lately, Victor has been actively involved in developing a technology that can remove carbon dioxide from the air and is much intrigued by all existing and also conceptual methods that can remove CO2 emissions. Victor will speak about his institutional roles and current position himself. So, dear Victor, the floor is all yours.
Thank you very much, Katja, and hello, welcome on board, everyone. Thank you for joining today. Some people keep joining, so hopefully no one will be late to the introduction, as we are already running a few minutes late. Sorry for that. I'd like to ask my partner in this, Tim from ISO Slovenia, to help me out with the presentations and the sharing of the screen. I see something is happening. Yes, I believe all of you can see the slides. So welcome again. This is a webinar, sort of a 101 starting course on carbon dioxide removal. And as already kindly introduced by Katja, my name is Victor. I'm from Hungary, Budapest, Hungary. However, today I'm talking to you from Brussels, Belgium. And I serve as a consultant for the Sustainaware project, which has the aim of non-formal education of young people on climate mitigation. We're basically creating tools, games, toolkits for games, activities, which can be used for climate change education. So the webinars are just one part of this project. We've had a summer school recently in Ljubljana at your university in July. I'm not sure, maybe we even have a couple of you who have participated in the course. I'm not sure. If you do, please give us a signal in the chat and say hi. Otherwise, we've had other outputs such as brochures, as well as, more importantly, I guess the main output we had during the course was a competence model, which is mainly aimed at youth workers, as well as educators of all kinds, who want to bring interactive, gamified tools to teach about climate change. So Tim, if I may ask you to jump to the next one, which is actually still about, yes, thank you very much. This is a webinar series, and it's actually the final episode of our webinar series. All our previous webinars are available online on ISO's YouTube channel. And just like this webinar, it's being recorded and it's going to be uploaded to YouTube, which you can watch later on. And you're also encouraged to watch our older ones. Thank you. Next one. So the Sustainaware project, as already introduced, is a project that is co-funded by the EU. More precisely, it's being funded by EUKI, which stands for European Climate Initiative. It's an initiative of a German ministry for climate affairs, for climate action and economic affairs. And their aim is to support climate action, climate mitigation in different regions of Europe. In this case, it's the CEE region, Central and Eastern Europe. Therefore, the focus region of our Sustainaware project is Hungary and Slovenia. Going on to the next one, we will jump straight into it. And I promise you, this is probably the most complex graph that we will have in this course. So don't get afraid, don't quit right now because of seeing complex graphs. I assume, knowing from Katja, that you are all aware of the problem, the one that we have since the Industrial Revolution. We humans have emitted more than 2,000 gigatons of carbon dioxide into the atmosphere. A gigaton is 1 billion metric tons. So I believe we all agree that the imperative for combating climate change is to curb emissions very fast, as fast as possible. For example, by ramping up renewable energy, boosting energy efficiency, stopping deforestation, and several other ways like curbing super pollutants like hydrofluorocarbons, HFCs. And what we're gonna discover today and talk more about is the fact that the latest climate science tells us, however, that these efforts, reducing emissions, alone aren't enough to prevent dangerous climate change. And to keep global warming to less than 1.5 to 2 degrees, scientists say it's necessary, which is the necessary temperature scenario to preventing the worst impacts of climate change. We need to remove carbon from the atmosphere and store it somewhere. So, in fact, most climate models and climate scenarios show we'll need to remove billions of metric tons annually by 2050, while also doing emission reductions in parallel. And this graph that you see here is actually taken as a screenshot taken from the latest IPCC report. The IPCC is the Intergovernmental Panel on Climate Change, the official scientific panel of the UN on the topic. And P1, P2, P3, and P4 gives different scenarios with a different amount of carbon removal needed and included in it. Meaning, the earlier we start to reduce emissions, the later and the smaller amount of removals we will need. However, if you look at P4, if we delay emission reductions and if we delay climate action, we will very much rely on technological carbon removal, which I think we all agree that is an unideal scenario. So to sum up and going to the next one, here is a graph on staying below 1.5 degrees Celsius as global warming. And this is sort of a notional scenario showing the role of carbon removal in bringing emissions to net zero by mid-century, 2100, which is consistent with limiting warming to 1.5 degrees. And it assumes concurrent mitigation of CO2 and non-CO2 gases like methane, and the faster and or deeper emission reductions could reduce the role of carbon removal, the methods that we're gonna talk about today. Slower and their weaker emission reductions would increase the need for that. So we will go through 6 carbon removal methods, and I think the time, this 1 hour, is really just enough to just go through them and give a real life example of them. But each carbon removal approach faces challenges and limitations. So let's dig in. First one, forests. Quite straightforward, right? Photosynthesis removes carbon dioxide annually and naturally. We all know that. And trees are especially good at storing carbon removed from the atmosphere by photosynthesis. So if we expand, restore, and manage forests to encourage more carbon uptake, we can leverage the power of photosynthesis, converting carbon dioxide in the air into carbon stored in wood and soils, right? We know the carbon cycle. There's an estimate that the carbon removal potential from forests and trees outside forests in the United States alone is more than 0.5 gigaton per year, which is equivalent to all annual emissions from the United States agricultural sector. So let's just stick with that example. The removal potential of forests and trees in the US is more than 0.5 gigaton per year, which is the same size as all yearly emissions from US agriculture. I just let that sink in. So these approaches to remove CO2 through forests can be relatively inexpensive compared to other methods that we will go through soon. And generally, if we are talking about carbon credits, carbon removal credits, we would say generally less than $50 per metric ton can be removed through tree planting. And it also has other benefits, as you know it. Trees clean the air, they clean the water, they have all kinds of environmental co-benefits. One major challenge, however, with forests is ensuring that the expansion of new forests in one place doesn't come at the expense of a forest somewhere else. So, for example, reforesting farmland would reduce the supply of food, right? It is a competition between land being used for food and land being used for trees and carbon removal. And one of my goals today is also to try to simulate somehow the potential of these methods through a scientific simulator. And I will try to keep switching to this simulator. Let me do that right now. It's a simulator that has been constantly being updated by MIT's Climate Interactive. It's a project of MIT Sloan School in Boston, Massachusetts. And En-ROADS is an open access tool. You can also open it. It's free. It can be found on the En-ROADS Climate Interactive website. And what it does, it simulates all kinds of measures like energy taxes, energy subsidies, and shows the global climate impacts like temperature rise. And it's based mainly on IPCC, IEA data, and it's constantly being updated. In case you want to change assumptions, you also have the option to change assumptions in the system, like climate system sensitivities. So it's don't feel like it's sticking to a certain or a given data or science. It's it can be customized to all kinds of different scenarios. So we have this button here on afforestation. Basically, we can simulate the temperature impact of increasing percentage of available land used for afforestation. So these are global measures that we see here. I just want to give you an impression. What if we would increase afforestation by 50% annually? Do you see a change happening? I'm pushing this replay button just for you to see. Imagine we are planting trees on all available land, increasing that by 50% of the available land. Does it have a big impact from 3.6, 3.5 centigrade? Also have to consider at what cost this 0.0 Celsius comes. What if we reset this whole thing and we simulate 100%? We still at 0.1 centigrade. Okay, now I'd like to ask Tim to switch back to the slides, and we'll continue. We'll come back to En-ROADS to see other methods as well being simulated here. All right, so next one. We're arriving at farms, soils naturally store carbon, right? But agricultural soils are running a big deficit due to the intensive use, as they are being used for constant cultivation. And because agricultural land is so expansive, more than 900 million acres in the United States. That's 900 million acres. That's 3,600,000 square kilometers. If we convert it in the United States alone, even small increases in soil carbon per acre could be very impactful. So we're talking about an impactful area when we're talking about agricultural land farms when it comes to carbon removal. However, building soil carbon is good for farmers and ranchers, as it can increase soil health and crop yields. And if you integrate trees on farms, you can also remove carbon while providing, for example, other benefits like shade and also forage for livestock. And there are also many ways to increase carbon in soils. For example, have you heard about planting cover crops? It's when fields are otherwise bare can extend photosynthesis throughout the year by sequestering about 0.5 metric ton of CO2 per acre per year. Also, if farmers are using compost, that can also improve yields while storing the compost's carbon content in the soil. Some scientists are also developing crops with deeper roots, making them more resistant to drought, while depositing also more carbon into the soil with the deeper roots. Managing soil for carbon at a larger scale, though, is tricky. it's a tricky proposition. Natural systems are inherently variable, and that makes it a real challenge to predict, measure, and monitor in the long term carbon benefits of any given practice on any given acre. It's a tough one to monitor. So the efficacy of some practices is also subject to a continued scientific debate. Let's see. Before I switch, I'm going to check what type of options we have in the En-ROADS simulator. Oh, yes, we have it. 1 second. I'm going to switch. So we're simulating agricultural soil carbon sequestration. I reset it. En-ROADS, let's see. What if we would maximize the potential, the percentage of max potential of agricultural soil carbon sequestration? Does it help? Pretty much the same as with afforestation and trees. You see in the bottom right corner the sources of net CO2 removals graph, and if I push replay button, you can see how much it has helped. You know what? Let's see. What if we leave the previous one on as well? That way, we will have a more diverse graph. So you see the green and the yellow one, we have both afforestation as well as maximizing agricultural soil carbon. We are now at 0.02 degrees Celsius. All right, let's see what if we only do removals and no reductions. Hopefully this will never happen. Okay, Tim, I'd like to ask you to switch back. Going on to the next one. There we go. Method number 3, bioenergy with carbon capture and storage, so-called as BECCS. So bioenergy with carbon capture and storage is another way to use photosynthesis in this. However, it's more complicated than planting trees or managing soils, and it doesn't always work for the climate. BECCS is the process of using biomass for energy in the industrial, power, or transportation sectors, capturing its emissions before they are released back into the atmosphere, and then storing that captured carbon either underground or in products like concrete. And if BECCS causes more biomass to grow than would otherwise, or stores more carbon instead of releasing it back into the atmosphere, then we can look at BECCS as a net carbon removal method. So if BECCS relies on bioenergy crops, it could displace food production or natural ecosystem, erasing climate benefits and also exacerbating food insecurity, ecosystem loss. So it's rather, there are a lot of ways to get it wrong for BECCS to deliver the expected climate benefits. So imagine you're just cutting trees or using biomass, you're burning it for energy, and at the same time you are putting sort of a filter on top of the chimney and capturing the CO2, which can be pumped into geological formations underground. We'll get back to that. You know what? Let's also simulate this in En-ROADS. Let me switch. Here we are. So, right there, bioenergy, carbon capture and storage. What if we would maximize? Whoa, 0.2 centigrade. Okay, we are this so far. This is the most impactful measure in En-ROADS, at least. Again, this is a global measure. Okay, and if you look at the left graph, you also see that we're not just removing carbon, but we are also adding energy into the energy mix by increasing bioenergy, right? Okay, let's leave it like that. I'd like to ask Tim again. Please come back to the, yes, thanks. So the next one, probably my, oh no, yes, before we jump to my favorite one, here is a case example. This facility is in Canada. It's a BACS. It's one of the, I think it's the first. It's a pioneer pilot project of BACS being used at large industrial level. Now, I'm asking you to spot the problematic factor on this picture. We talked about biomass, right? Talked about wood. But I cannot unsee that big pile of black coal behind the facility. So BACS is being used here on a coal plant, which is yeah, it's great that they are capturing the emissions of a coal plant, but on the other hand, it shouldn't incentivize the burning of more coal, right? We know it's one of the major factors, one of the most carbon intensive ways of producing energy is by burning coal. So that's what that's where we are ending up with. It's BACS as it is being used is probably not the most ideal carbon removal method. All right, going to the next one. Direct air capture technology. And here, I'd like to mention that in parallel with working on this Sustainaware project, I work as a project manager in a startup in Hungary, and we are developing a direct air capture technology. It's the process of chemically scrubbing carbon dioxide directly from ambient air and then storing it either underground or also long-lived products. It's a very new technology. It's similar to the carbon capture and storage technology used to capture emissions from sources like power plants and industrial facilities. However, the difference is that direct air capture removes excess carbon directly from the atmosphere instead of capturing it at the source. It is relatively straightforward to measure and account for the climate benefits of direct air capture, and its potential scale of deployment is pretty big. But the technology, unfortunately, today remains very costly and very energy intensive. So we don't want to have, right, a carbon removal technology which needs a lot of energy, because then it's contradicting. We're not solving the problem by needing a lot of energy to operate such a plant. There was a study in 2018, I think, that estimates that it would cost about $100 to $200 per metric ton of direct air capture removals. However, as there is constantly research and investment being pumped into this technology, and also there is a lot of interest for DAC lately. The price has gone up, so the range of costs for DAC varies between $250 and $600 today, depending on the technology choice, the low carbon energy source, and also the scale of their deployment. Again, can you remember the cost of planting trees for carbon removal? $50. $50 versus $250 to $600. However, we know R&D and innovation, investing in the technology today will make it cheaper and more affordable in the future. And I think one of the best examples is solar. So, you know where first solar was used? On calculators. Today we're using it to produce electricity. It took a while, but investments and further R&D has made it possible to generate electricity with the tiny little solar panel, which you all remember probably from pocket calculators. I'm actually going to turn on the light. So the plan, or the picture that you see here, is in Iceland, and there's a good reason why. Iceland has a lot of geothermal energy, and this technology that they use at Climeworks relies on geothermal heat. We can also get into that. So this one in Iceland is currently the only direct air capture facility which is at a commercial stage. There are a handful of others developing and getting there, but right now this is the only commercial one, and it needs substantial heat and power inputs. Scrubbing 1 gigaton of carbon dioxide from the air could require nearly 10% of today's total energy consumption. And the direct air capture technology would also need to be powered by low or zero carbon energy sources to actually result in net carbon removal. As said, investment into development and deployment, together with continued progress of deployment of cheap, clean energy, could really advance the prospects for direct air capture at a large scale. So multiple companies have already developed systems, multiple companies have invested in such systems. Just to name a few: Shopify, Microsoft, Amazon, Facebook, McKinsey. They are all pouring money into this field to basically to secure themselves carbon removals to offset their future emissions. And if we go to the next slide, this is me standing in Switzerland at the world's very first direct air capture facility. It's close to Zurich in Switzerland, and it's an exciting one, because if you go to the next slide, you will see how it works. These ventilators are being put on top of a waste incinerator. So they are using the heat from the waste incinerator. They're using excess heat, which would otherwise go waste. And the CO2 that's being captured is feeding a small greenhouse next to the facility where they are growing tomatoes and cucumbers, and it increases the growth of plants in a closed greenhouse. When you ask how such technologies work, imagine basically a fan that's sucking air and it's pushing it through a filter material. There are two types of filters, either a solid sorbent, which is in most cases, it's something like a polymer, or something like a cloth type of material, just to give an example, or it's a liquid solvent. The Swiss Icelandic company, they are using a solid sorbent, and the part where they need a lot of heat is the desorption part, where they are desorbing the captured CO2 from the filter material. And now here comes the brand pitch, why our technology in Hungary is better. No, just joking. We are working with solid sorbent, kind of I don't know if you ever opened up a kitchen water filter. You know, you have there are these kitchen water filters, for example, Brita, and their filters work with polymers and active coal. And the type of solid sorbent that we use for filter is very, very similar to those little polymer balls used in these water filters. And the cool thing about them is that they can selectively bond carbon dioxide if you treat it with the right chemical in advance. And our technology is based on a humidity swing method, which means that we don't need heat or voltage in order to decrease CO2, release the CO2 from the material. We apply water vapor humidity to finish the cycles. So we are at a very early stage. We have basically a validated laboratory proof of concept, and right now we're finishing our table size prototype. So early days for us, however, very exciting. Hence the reason why I am in Brussels today to find investors for this technology. All right, so the bottom line is that direct air capture is still a new technology, and while it shows enormous potential for scaling up, these systems are the first of their kind, and they really need public support to advance it. So let's try it, and let's simulate it in En-ROADS. Okay, direct air capture, increasing the percentage of max potential. Oh, this is embarrassing. Didn't help a lot. What if I restart the whole thing? Let's see. What if we started from scratch? We only do direct architecture. Okay. Okay. Again, similarly with others, we have 0.1. And now you might ask yourself, how come that together with other measures, it's not as visible as done alone? It's because the way this simulator works is that by the time you have a lot of multiple areas of action, things get a bit complicated. And I don't want to get into that, but we see I'm just gonna go back to apply all of them so that we can have some sort of optimism for carbon removals. Let's see if we do biochar. And we had afforestation. Right, here we were. So 3.2, we started from 3.6. We're applying expensive technologies. Okay, Tim, can we please switch back? Thanks. So, oh yeah, I wanted to show you. Tim, can you please play this video? Just our lab prototype. If you scroll to approximately the middle, I think we will see. It's me explaining how it works. Scroll a bit more, please. Almost there. Yep. So if you stop here, this is the lab version. So imagine this. It starts from here, a lab version, hopefully one day to a facility. We needed this part in order to validate that the concept works. The concept works that we are capturing CO2 at an efficient rate with this polymer, and we're trying to simulate this in a bigger version, a table size version, which can be put into a outdoor environment and not in a closed laboratory setting. All right, thanks, Tim. We can go to the next one. Now it's getting complicated. Yes, slides. So carbon mineralization, and I think most of you are geography students, so perhaps this is your topic. So we know that some minerals naturally react with CO2, turning carbon from a gas into a solid. The process is commonly referred to as carbon mineralization, or it's also called enhanced feathering. And it naturally happens very slowly over hundreds or thousands of years. Scientists are figuring out how to speed up the carbon mineralization process, especially by enhancing the exposure of these minerals to CO2 in air or in ocean. That could mean, in real life, pumping alkaline spring water from underground to the surface, where minerals can react with the air, moving air through large deposits of mine tailings, for example, rocks left over from mining operations that contain the right mineral composition. It could also entail the crushing or developing enzymes that chew up mineral deposits to increase their surface area, and also finding ways to weather certain industrial byproducts like fly ash or kiln dust or iron and steel slag. So it has been shown that carbon mineralization is possible, and actually there are a handful of startups already developing mineralization-based building materials, but there is definitely more work to be done to map out cost-effective and prudent applications for scaled deployment. All right, so let me see if we have this in En-ROADS. Yes, we do. What do we do is switch. Okay, here we go. Enhanced mineralization, 100%. Again, 0.1 degree. We started from 3.6 and we are maximizing all carbon removal methods, doing nothing else, not touching any energy policy. We're just removing. You see on the graph, we applied already planting of trees. We applied bioenergy with carbon capture and storage. We applied direct air capture. We applied mineralization and agricultural soil carbon. Okay, let's switch back to the slides, get a little bit of guidance. Yes, I think this is an interesting one to look into, just for you to get a sense how, if you click the image, the video will start, I think. And so a company in Iceland called Carbfix is doing this by basically speeding up the process. They are mixing captured CO2 with water and basically making a soda water, a very fizzy soda water that they are pumping into deep basaltic layers. And with this process of mixing the CO2 in a liquid form into basaltic rock, they speed up the mineralization of CO2, and they are claiming that they can do this mineralization within 2 years, which would otherwise take much longer. And here here it is, 2 years, showing their samples of basaltic formations, rock formations. And by the way, they are collaborating with this Swiss company called Climeworks, doing direct air capture, and they are pairing their technologies, capturing carbon from the air and using this one to store it. So ocean-based concepts. There are a number of ocean-based carbon removal concepts that have been proposed to leverage the ocean's capacity to store carbon, and also there have been many approaches to identify more of these beyond land, sort of like a farming on the oceans. Sounds bad, but however, nearly all of them are at very early stages of deployment, and they need more research, and in some cases also pilot testing to understand whether they are appropriate for investment given ecological, social, governance impact. So each ocean-based carbon removal approach aims to accelerate the natural carbon cycles in the ocean. They could include leveraging photosynthesis in coastal plants, or seaweed, or phytoplankton. It could also be adding certain minerals to increase storage of dissolved bicarbonate. Or it could also be running an electric current through seawater to help extract CO2. And some ocean-based removal options could also provide co-benefits. So, for example, coastal blue carbon and seaweed cultivation could remove carbon while also supporting ecosystem restoration and adding minerals to help the ocean store carbon. Could also reduce the acidification of the ocean, which is also a consequence of climate change. However, much is still unknown about the ecological impact of these approaches, and further research is needed to better understand potential risks before these approaches are even applied at any scale in the oceans. And in the near term, cultivated seaweed can be a good approach by using the picture you see here is a seaweed farm or kelp farm, and kelp can be used for food, fuel, fertilizer. Obviously, if you eat it or burn it or use it as a fertilizer, it will not result in carbon removal, but it can reduce emissions compared to conventional production of fertilizer, for example. And it can also provide an economic return that supports the growth of the larger industry. Then an interesting one, for example, is that there is this red type of seaweed, this red type of kelp, which can be cultivated in the way as you see it on the screen. And if you feed it to cows, they burp less methane. So that can have, well, not a removal effect, but it's also an emission reductions effect on methane in the atmosphere, which is a we're not talking about CO2, but we're talking about very potent greenhouse gas when we talk about methane. So there are quite a few areas which can be explored with ocean-based concepts. And also, if you let seaweed grow, and if you don't produce food, fuel, or fertilizer out of it, but you sort of let it die and sink to the bottom of the ocean, that way you're contributing to carbon removal by basically contributing to the natural carbon cycle. However, who would do this? Why would someone do this? It's costly, it takes a lot of effort, and it's, well, almost impossible to monitor and verify how much carbon is being removed. All right, this one we cannot test in En-ROADS. So to sum up, going to the next slide. This is a video again of ocean-based methods, and we can look into it. I suggest we scroll in a little bit, maybe a minute or so. Can you add sound? We need to tweak Zoom, but doesn't matter. So yeah, weathering of rock washes alkali molecules into the ocean, thereby converting the salt CO2 into bicarbonate. This is part of the natural cycle. However, this could also be artificially increased. this is basically seaweed cultivation, where you're adding minerals, seaweed, and thereby increasing the cycle, having some co-benefits of ecosystems benefiting around it, from it, like fish, phytoplankton. Here it is. Gives actually a good picture of how these floating farms could look like. Artificial booming of phytoplankton in the oceans. You know, one of the biggest limitations of all these that you see here is actually we're talking about climate action here, but still all this activity is increasing farming activities in the ocean. So it could also look like we are moving farms, monocultures into the sea. And I have the impression that a lot of people do not like this idea. Public, I mean, the wider public. So it does face a lot of opposition, actually, to increase such activities in the oceans. Also, when it comes to lobbying powers, one of the biggest competition for these approaches that you see here are large-scale fishing industry. It's and also shipping. All these measures are competing with their environment and their profits. So so when it comes to the feasibility, it does face serious challenges. All right, thanks. Going back to the slides, we are summing up carbon removal methods. We had forests, farms, we had bioenergy with carbon capture and storage, BECCS, we had direct air capture, carbon mineralization, ocean-based concepts, and we still missed quite a few, but this is what we had enough time for. And actually, if you still have the interest to stay for a couple of minutes, this is the time for a Q&A, question and answer session. I would be really curious to hear your questions, remarks, if you have any. Perhaps you can raise your hand in Zoom. There is this option, and we'll take your question.
Victor, we have a question here for you from the audience.
Mm-hmm.
Hello.
Hi.
Great presentation. Really intriguing about the whole filter systems, but I have a question about those filters that you mentioned. How recyclable are they, and what is the real cost of producing those filters? How much can you use them? And you were talking about polymers. You know, you're again talking about fossil fuels. I know we can't go without them, but how recyclable are they? Thank you.
Very good point. Thanks for posing this question. So yes, right. What are the resources needed in order to make this happen? When it comes to our technology and our polymer, we know that every day we have 80 cycles a day. That's the biggest efficiency that we can work. This means our system is being turned on 24 hours long, 80 cycles a day. The polymer can do 2,000 cycles. So you can do the math for how long a batch of polymer is good for. It has its lifetime, it's limited. However, we recently discovered this because this is an important question, that these polymers can be turned into a sort of charcoal, biochar. And we didn't mention biochar as a carbon removal method, but you achieve biochar basically if you take any type of biomass and you put it in a oven, a special oven. It's called a pyrolysis oven. Probably you are familiar with pyrolysis. So it's basically baking stuff in an environment without oxygen. And this causes the effect that all the residues, all the fats, all the oils are basically evaporating, and you end up with nothing else, just a pure carbon content. So you bake biomass, or in this case, our polymer, into a charcoal, which is very stable. So if you, I don't know, dig it underground, it will remain there for thousands of years, and it will store carbon dioxide. Putting it underground is just one way of dealing with it. It can be used for agroforestry and agriculture as a type of fertilizer. But also there are now companies who are using biochar for concrete. They are putting this biochar into their cement mixes, meaning that less cement is needed. We know cement production creates CO2. So in that way, CO2 emissions can be reduced. And also some companies say that the concrete that they end up with is more robust, more stronger, with these biochar particles in it. So our plan is to pyrolyze our polymer and turn it into a biochar. What we can do with that biochar is still up to a question, and we are exploring that. As said, we are at a very early stage, and this is an important question actually, because all the investors are asking this question, and they won't finance something that's using that's creating waste, dangerous waste. So it's something that has to be figured out.
Thank you very much for this answer. Very interesting, the whole presentation. And I see smiling, happy faces here in the room. Does anyone else have a question? Those of you online?
Yes, hi. First of all, thank you very much for this informative presentation. It was very nice. And my question is about carbon storage underground without mineralization. What effects does it have on the environment?
Yeah, so the only other way of geological storage, to my knowledge, is using empty oil and gas fields. it has a term. It's called the enhanced oil recovery. It sounds very bad. Why? Because oil companies are using this method, or have been using this method to extract even more oil. They use CO2, they pump it into empty reservoirs, and with the help of CO2, they are extracting even more. However, this can also be done to not to generate more oil, but to just store the gaseous CO2 in those empty reservoirs. However, this only works if there is a very strong cap rock that will ensure that there is no leakage of this gaseous CO2 from the empty reservoirs. Environmental NGOs, green NGOs are very much against this method because it's hard to ensure that the cap rock will safely store the CO2. However, the oil industry continuously says that if the cap rock is strong enough, it can be stored securely forever. I don't know if this answers your question.
Yes, it does. Thank you very much.
Sure. Any more thoughts? Doesn't have to be a question. It can be a thought, a remark as well. Something that you heard, you saw.
Yes, Victor, maybe a thought or two. Now seeing all these possibilities of carbon dioxide removal, I was wondering, what's the danger to rely on non-existing or pioneer technologies to postpone other measures, of course, climate change mitigation measures, in order to achieve very ambitious goals that European Union or Europe in general has in this regard? Because these technologies, they sound like very nice excuse to do nothing.
Yeah, yeah. And a lot of the public perception is exactly this, that a lot of people are afraid that even the discussion on carbon removals will hinder action right now. So I think a good example, actually now I'm talking against myself because obviously I'm biased, I'm into this, but a good example is nuclear energy. Back in, I don't even know when was nuclear energy brought to commercial stage. Many years ago, at least 60 years ago, no more. Back then they thought, okay, we will use nuclear energy for electricity generation, and we will find out how to deal with the nuclear waste. By the time this is going to be a problem, we will find it out. We're still here with nuclear energy and no real solution for dealing with the waste. And at the same time, I think we have wasted a lot of time by not researching, not developing enough energy sources. I mean, we have wind, solar, renewables. They are right behind me, but they are very far from perfect. They are very far from perfect, and it's going to be a miracle if we can solve this problem with only these. And we have wasted a lot of precious time to commercialize cool energy solutions.
Yes, I agree. And that leads us to the next question. That is, how can active citizens contribute to CO2 removal?
Tough one. Very tough one. I would say one way to do that is seek products, services, and companies who have a strategy for net zero. Because net zero, if a company says today, we are going net zero, the only way they can actually do that is through removals or with the help of removals. A company can reduce its emissions, can change their car fleet, they can change their offices, they can fly less, but at the end of the day, they will end up with some emissions, and the only way to offset those is through removals, either forests or either very expensive technologies. One way of contributing to innovation is to seek those services, companies which do have a vision for net zero, a meaningful vision for net zero. And also, I think one of the things that you can do most is enhancing the public debate by talking about it, by researching it. There's a lot of need for research in this space, and you as students, academics, are best placed to add to this by generating meaningful studies.
Thank you. We like to hear that. Any other questions here from our lecture room? No.
Yes, I have another question or thought.
Yes.
So when we were talking about the direct air capture technology, all the implementations are taking place on the surface. However, due to my understanding of carbon sinking in the atmosphere, this all happens at the higher elevations, let's say, around 10 or 20 kilometers, where there's enough water vapor due to just store it, or how would I say that, the clouds are formed and so on. So wouldn't it be more effective to implement those technologies somewhere above? And that's why also I think on the chart that there wasn't much of a change if we implement it on the surface. If like, this was just my thought, so if you can correct me.
Actually, CO2 is the same in the atmosphere. It's the same here on our level in the room and up there. It's very dilute. CO2 is very dilute in the air. It's 400 ppm, meaning 0.00%. This is why direct air capture is so expensive, because we are trying to filter something that's very dilute in the air. So it doesn't matter actually if you are high up there or if you are right next to a coal plant. The amount of CO2 is the same unless you put it right on the chimney, but then you are not taking away anthropogenic legacy CO2 emissions, but you're just avoiding that chimney to put even more into the atmosphere.
Okay, yeah, thanks.
Thanks for the question. Yeah, I'd like to encourage you to if you have LinkedIn, add me on LinkedIn, and you'll see a lot of posts. I try to be very active with sharing these things and also learning from others on LinkedIn. Or if you have email, you have a more complex question that we can both look at, then shoot me an email.
Victor, on behalf of everyone here and online, I would like to thank you. Thank you for your time, your energy and optimism and encouragement for all of us to find new solutions.
Yes, thank you very much. Thank you very much for the opportunity, and mostly thank you for your attention in taking part for this. And we would very much appreciate if you could share how you felt during this webinar and what you learned from it by filling a survey. I promise it's a very short one. We will put it in the chat right now, and this would help us a lot with our Sustainaware project. Thanks for doing that, or I can also send it to Katja, and Katja can share it with the whole group. Again, thanks, and best of luck and best of success with your studies.
Thank you, Victor. Thank you very much.